Picture this, a place where gravity is so powerful, not even light can escape its clutches, where the laws of physics, as we know them, twist and shatter into oblivion. Black holes aren't just cosmic vacuum cleaners lurking in the void. They're the universe's most enigmatic paradoxes, defying everything we think we know about space, time, and reality itself. And here's the kicker: scientists estimate there could be over 100 million black holes in our galaxy alone, yet we've barely scratched the surface of their secrets. What if I told you that black holes might not even be holes at all, or that some of them could be older than time as we measure it? These celestial monsters aren't just destroying stars, they're reshaping galaxies, bending the fabric of space-time, and possibly holding the keys to understanding the very origins of existence. And yet, for all their terrifying power, there's something almost poetic about them, the ultimate cosmic mystery lurking in plain sight. That's why today we're diving headfirst into the abyss to uncover 30 of the most mind-blowing, lesser-known truths about black holes, facts so strange they'll make you question everything you thought you knew. From black holes that sing to ones that might be portals to other universes, we're peeling back the curtain on these cosmic anomalies. So buckle up. By the end of this journey, you won't just see black holes as ominous voids, you'll see them as the universe's most fascinating storytellers. Ready to unravel the mystery? Let's begin. Black holes might seem like silent voids in space, but they're actually cosmic musicians capable of producing eerie, otherworldly songs. Here's how it works. When a black hole pulls in matter from its surroundings, it doesn't just vanish without a trace. The gas and dust swirling toward the event horizon get superheated, creating immense pressure waves that ripple through nearby gas clouds. These waves vibrate at frequencies so low they would be impossible for human ears to hear naturally. But with the right technology, scientists can translate them into sound, and what they've discovered is haunting. The Chandra X-ray Observatory captured one of these cosmic performances from a black hole over 250 million light-years away. By mapping the pressure waves in the Perseus galaxy cluster, researchers converted them into audible notes, shifting the frequencies up by 57 octaves. Yes, you heard that right, 57, to bring them into the range of human hearing. The result, a deep, resonant hum, like the lowest note on a piano played in slow motion, reverberating through the void. It's not exactly a catchy tune, but it's proof that even the darkest corners of the universe aren't silent. What's even wilder, these sound waves aren't just for show. They might actually play a role in shaping galaxies. The energy from these vibrations can heat up surrounding gas, preventing it from cooling and collapsing into new stars, effectively putting a cosmic pause button on star formation. So in a way, black holes don't just destroy, they conduct the universe's symphony, orchestrating the life cycles of galaxies with their deep, ghostly songs. Imagine that, a celestial maestro lurking in the dark, setting the rhythm for everything around it. And if you think that's strange, just wait until you hear about the black holes that spin so fast they warp space-time itself into knots. But that's a story for another moment. What if you could stand at the edge of a black hole and watch time itself stretch like taffy? Einstein's theory of relativity reveals something downright bizarre. The closer you get to a black hole's event horizon, the slower time ticks for you compared to someone far away. Imagine holding a clock in one hand while falling toward the abyss. Your clock would crawl while clocks back on Earth raced ahead. This isn't science fiction. It's gravitational time dilation in action, where gravity so intense warps the very fabric of space-time. The movie Interstellar nailed this concept with its iconic water planet scene. Remember how 1 hour there equaled 7 years back on the ship? That's not Hollywood exaggeration, it's physics. Near a supermassive black hole like Gargantua, the gravitational pull is so extreme that time bends to its will. For an astronaut orbiting just outside the event horizon, minutes could pass while decades fly by elsewhere in the universe. It's a one-way trip into the future with no return ticket. Here's where it gets even weirder. If you could somehow hover at the edge of a black hole and peer out toward the cosmos, you'd see the universe speed up like a fast-forwarded movie. Stars would birth and die in flashes, galaxies would collide in blinks, all while you're stuck in this eerie slow-motion existence. But try to shout a warning to the outside world. Forget it, the light from your voice would take so long to escape the gravitational grip. Your message might not arrive for centuries, and don't think this is some far-off phenomenon. Even here on Earth, time dilation happens just on a microscopic scale. GPS satellites have to account for it because their clocks tick slightly faster in Earth's weaker gravity than those on the ground. But near a black hole, the effect is so dramatic it rewrites the rules of reality. Picture two twins, one stays home, the other ventures near a black hole. When the traveler returns, they might be just a year older while their sibling has aged a lifetime. It's the ultimate cosmic time machine, no DeLorean required. What's truly mind-bending? From the perspective of someone inside a black hole, time might feel normal. But to the outside universe, you're frozen in time forever at the event horizon, like a ghost in the cosmic machinery. This isn't just about clocks slowing down, it's about how gravity doesn't just pull on matter. It twists time itself into knots, and if that doesn't make you question everything, wait until you hear about the black holes that might be hiding entire universes inside them. Here's something that might shatter your cosmic worldview. Black holes aren't holes at all. That name, a total misdirection. Imagine calling a mountain a pit because it's tall enough to cast a shadow. The truth is far stranger. A black hole is an almost unfathomably dense singularity, a point where matter has been crushed so violently by gravity, it warps space and time into a bottomless well. Think of it like taking the entire mass of a star 20 times heavier than our sun and squeezing it into a space smaller than New York City. The result? A gravitational monster so powerful, it pins the fabric of reality itself to the breaking point. Picture a cosmic vacuum cleaner, but instead of sucking up dust bunnies, it devours light. That's the event horizon, the infamous point of no return where gravity wins forever. Cross it, and not even photons racing at 670 million miles per hour can escape. But here's the twist, the event horizon isn't a physical surface. It's more like a mathematical boundary, a ripple in space-time marking where the universe's rulebook gets tossed out the window. And at the center, that singularity, a place so crushed our laws of physics just stop working. To grasp how bizarre this is, consider a crushed soda can. You can dent it, but there's always some empty space between the atoms. Now imagine crushing it with the force of a collapsing star until every gap vanishes, until even atoms collapse into a soup of quarks and gluons. That's a black hole's core, not a hole but a thing so dense it bends space-time into a closed loop. If you fell in and somehow survived the tidal forces spaghetti-fying your body, you wouldn't hit a bottom. You'd just keep falling, trapped in a warped reality where down loses all meaning. And here's the kicker. This isn't some far-fetched theory. We've seen the shadow of a black hole's event horizon thanks to the Event Horizon Telescope's image of Messier 87, a supermassive beast weighing 6.5 billion suns. That glowing ring, not the hole itself, but light bent into a cosmic funhouse mirror by the black hole's gravity. The darkness in the center, that's the shadow of the event horizon, a silent testament to the fact that black holes aren't empty voids. They're the universe's most extreme prisons where matter doesn't just disappear. It gets rewritten into something beyond our comprehension. So next time you hear black hole, forget the idea of a dark tunnel. Picture instead a dying star's last, defiant act, a gravitational tantrum so fierce, it punches a permanent dent in the cosmos. And if that doesn't make you rethink everything, wait until you learn how some black holes might be older than the universe itself. Hold onto your seats for this one. Some black holes spin so fast they make a tornado look like a gentle breeze. We're talking about a cosmic phenomenon called frame dragging, where a rotating black hole doesn't just pull in matter. It yanks space-time itself into a swirling vortex like stirring honey with a giant invisible spoon. And the champion of this extreme behavior, a black hole named GRS 1915 plus 105, clocking in at over 1,000 rotations per second. That's not just fast, it's close to the universe's ultimate speed limit where space and time get twisted into knots. Think of space-time as a stretchy fabric. A stationary black hole simply bends it like a bowling ball sitting on a trampoline, but a spinning one, it's more like dragging that bowling ball in circles until the fabric spirals around it. This effect gets so extreme near the event horizon that if you tried to stand still, you'd be swept along like a leaf caught in a river's current, not because you're moving, but because space itself is being dragged around you. Astronomers call this the ergosphere, a region where space is whirling so violently, even light can't resist the pull. Now, GRS 1915 plus 105 takes this to ludicrous extremes. Imagine a black hole with the mass of 14 suns spinning at nearly the speed of light. At that rate, the singularity inside isn't just a point, it flattens into a disk like pizza dough spun too fast. This breaks the usual rules, stretching space-time so thin that time practically grinds to a halt at the poles while racing forward at the equator. It's the cosmic equivalent of a runaway merry-go-round, where the laws of physics start to blur at the edges. What's wilder, these spinning monsters might hold the key to powering the universe's most energetic explosions. As their rotation twists magnetic fields into cosmic slingshots, they can launch jets of plasma at nearly light speed, visible across billions of light years. So while black holes are often painted as destroyers, their spin reveals another side: celestial power plants, shaping galaxies with every furious rotation. And if that doesn't leave you dizzy, consider this. Some theories suggest a black hole spinning fast enough could rip open a tunnel to, well, let's just say elsewhere. But that's a mystery for another moment. When we think of black holes, our minds usually jump to cosmic titans, supermassive monsters like Sagittarius A, weighing millions of suns. But what if I told you some black holes could be smaller than a grapefruit? These hypothetical specks of doom are called primordial black holes, and they might have been born in the chaos of the Big Bang itself. Imagine all the crushing gravitational force of a black hole packed into something you could hold in your hand. One wrong move and poof, you've got a singularity in your living room. The theory goes like this. In the first fraction of a second after the Big Bang, fluctuations in the newborn universe could have created regions so dense they collapsed directly into black holes, no dying star required. Some might have been as massive as mountains, others as light as asteroids. But here's where it gets wild. The tiniest of them could still be around today, hiding in the cosmos like invisible landmines. A primordial black hole the size of a tennis ball would weigh as much as Earth. Its gravity so intense it could shred you atom by atom if you got within a few feet. And they might not just be cosmic oddities, they could solve one of astronomy's biggest mysteries, dark matter. If enough of these tiny terrors exist, their combined gravity might explain why galaxies rotate faster than visible matter can account for. No exotic particles needed, just swarms of ancient black holes lurking unseen since the dawn of time. But there's a catch. According to Stephen Hawking, small black holes shouldn't last forever. They evaporate thanks to quantum effects near the event horizon that slowly bleed away their mass, a process called Hawking radiation. A grapefruit-sized primordial black hole would be nearing the end of its life now after 13.8 billion years. Its death throes, a final, furious burst of gamma rays brighter than 1,000 suns. Astronomers are scanning the skies for these telltale flashes, proof that the universe is littered with invisible time bombs from its very first moments. So next time you gaze at the night sky, consider this. Somewhere out there, a black hole smaller than a pumpkin might be silently dissolving into nothingness. its last whisper a fleeting spark in the dark. And if scientists ever catch that signal, it could rewrite our understanding of everything, from the Big Bang's aftermath to the hidden architecture of reality itself. Not bad for something you could theoretically drop into a backpack if you dared. Now, let's talk about the black holes that defy evaporation, the ones growing so fast they could outlive the universe itself. Some of the most advanced civilizations in the universe might not live near stars. They could be orbiting black holes instead. The Kardashev scale, a method for ranking a civilization's technological prowess, suggests that truly advanced societies would need energy sources far beyond anything we can imagine. A Type 2 civilization, for example, might build a Dyson sphere to harness all the energy of their home star, but a Type 3 civilization, they'd likely graduate to something far more extreme, tapping into the mind-bending power of black holes. Enter the Penrose process, a way to steal energy from a spinning black hole's ergosphere, that whirling region of twisted space-time we mentioned earlier. Here's how it works. If you could fire a projectile into the ergosphere just right, the black hole's rotation would give it a speed boost so violent, it could escape with more energy than it arrived with. It's like bouncing a tennis ball off a moving freight train. The ball comes back faster because it stole some of the train's momentum. Advanced aliens might use this trick to siphon off unfathomable amounts of energy, turning black holes into cosmic power plants. But why stop there? Imagine a Dyson swarm not around a star but around a black hole's accretion disk. The superheated matter spiraling into the event horizon glows hotter than any star, emitting enough energy to power entire galaxies. A sufficiently advanced civilization could build orbital megastructures to capture that radiation, or even harvest the black hole's Hawking radiation as it evaporates. The numbers are staggering. A single stellar mass black hole could provide 10,000 times more energy than our Sun over its lifetime. And then there's the ultimate power play, feeding a black hole with controlled streams of matter to keep it emitting energy for billions of years. Some theoretical designs suggest dropping asteroids into the accretion disk at precise intervals, creating a steady energy output like clockwork. It's the universe's most dangerous battery. One wrong move, and your entire civilization becomes part of the menu. The craziest part, we might already have seen evidence of this. Mysterious flashes from distant quasars, supermassive black holes shining brighter than entire galaxies, could be signs of cosmic engineering on a scale we can barely fathom. Or perhaps they're just natural phenomena we don't yet understand. Either way, the idea remains. If you're an alien civilization looking for the ultimate energy source, you'd skip stars entirely and go straight for the darkest, hungriest objects in the cosmos. Because in a universe where survival means thinking big, black holes aren't just destroyers, they're the ultimate power outlets. Now, let's talk about the black holes that might be hiding something even stranger inside them. Not just energy, but entire universes. The giant lurking at the heart of our Milky Way isn't just another anonymous black hole. It's a cosmic celebrity with a name straight out of a sci-fi novel, Sagittarius A. Pronounced Sagittarius A, this supermassive beast weighs in at a staggering 4 million times the mass of our Sun, packed into a space no wider than the orbit of Mercury. But here's the twist, we wouldn't even know it existed if not for a group of stars caught in an endless dance around nothing. The story of its discovery reads like a galactic detective novel. For decades, astronomers noticed something odd. A cluster of stars near the galaxy's center was zipping around at breakneck speeds, as if tethered to an invisible anchor. One star in particular, nicknamed S2, became the key witness. It completes a full orbit every 16 years, reaching speeds of over 11 million miles per hour, nearly 3% the speed of light. Tracking its path revealed the culprit, an invisible gravitational monster so precise in its pull, it could only be a supermassive black hole. The research was so groundbreaking, it earned astronomers Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics. Using infrared telescopes to peer through the cosmic dust shrouding the galactic center, they mapped these stellar orbits with pinpoint accuracy, confirming Sagittarius A star's existence beyond doubt. But the quirks don't stop there. This black hole is oddly quiet compared to its flashy cousins in other galaxies. No roaring jets of plasma, just the occasional burp of X-rays. Scientists think it might be on a cosmic diet, starving due to a lack of nearby matter to devour. And then there's the name. Sagittarius A star sounds like something from a space opera, but it's actually a mundane label from radio astronomy. The A marks it as the brightest radio source in the constellation Sagittarius, and the star distinguishes it from a nearby cloud of gas. Not exactly glamorous, but fitting for an object that spent billions of years hiding in plain sight. Here's the kicker: Sagittarius A star might not be alone. Some theories suggest it could have smaller black hole companions orbiting it like planets around a sun, a hidden celestial family waiting to be discovered. So next time you look toward the constellation Sagittarius, remember, you're staring straight at the silent giant holding our galaxy together. And if that doesn't make you feel tiny, consider this: it's currently snacking on a mysterious spaghetti-like object called X7. But that's a story for another moment. Black holes might devour everything in their path, but they're not always neat eaters. Sometimes they vomit violently. Enter spaghettification, one of the universe's most horrifying yet mesmerizing processes. When a star or gas cloud strays too close to a black hole, the difference in gravity between the near and far sides becomes so extreme, it stretches the object into a long, thin strand of atoms, like cosmic taffy pulled apart by an invisible hand. But here's the twist: not all of that stretched material gets swallowed. Some of it gets launched back into space at nearly the speed of light in blazing jets that can span millions of light years. Take the supermassive black hole at the heart of galaxy Messier 87, the first ever photographed. While its event horizon may seem like a one-way ticket to oblivion, its poles tell a different story. As matter spirals toward the black hole, intense magnetic fields and centrifugal forces sling some of it away from the event horizon, channeling it into twin jets of superheated plasma. These jets aren't just dribbles, they're cosmic fire hoses, shooting particles across intergalactic space with enough energy to outshine entire galaxies. The one in M87 stretches 5,000 light-years into the void, a testament to the black hole's messy eating habits. What's truly wild is how these jets defy intuition. You'd think matter falling toward a black hole would vanish without a trace, but the extreme physics near the event horizon creates a sort of cosmic traffic jam. Particles collide, magnetic fields twist into knots, and the energy has to go somewhere. The result, a violent escape route along the black hole's rotational axis, where matter gets blasted into space fast enough to circle Earth 7 times in a single second. It's like a toddler flinging food, except here, the food is superheated gas moving at 99.9% the speed of light, and these jets aren't just for show. They sculpt their surroundings, carving out bubbles in intergalactic gas and influencing star formation across entire galaxy clusters. The black hole in M87 even provided humanity with its first glimpse of a black hole shadow, but its jets have been dazzling astronomers for decades. So next time you picture a black hole as a cosmic vacuum, remember, it's more like a messy toddler with a fire hose devouring with one hand while flinging leftovers across the universe with the other. But if you think that's chaotic, wait until you hear about the black holes that spin so fast they turn space-time into a funhouse mirror. Some black holes don't just sit quietly at the center of their galaxies, they run. Imagine a cosmic fugitive, a supermassive black hole ejected from its home and barreling through the void at 5 million miles per hour. That's not science fiction, it's the bizarre reality of a rogue black hole named 3C186, first spotted in 2017 as a streak of light stretching 200,000 light-years across space. This isn't a star or a gas cloud. It's an entire black hole weighing 1 billion suns, fleeing its galaxy like it's being chased. So how does something so monstrous get kicked out of its galactic neighborhood? The answer lies in a cosmic demolition derby. When two galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational dance. In most cases, they merge, but sometimes if a third black hole enters the mix, the chaotic three-body interaction can fling one of them into the abyss. Picture a game of billiards where one ball gets launched off the table at unimaginable speeds. That's essentially what happened to 3C186. It lost the gravitational tug of war and went careening into intergalactic space, trailing a wake of shocked gas and young stars behind it like cosmic breadcrumbs. What's even wilder, the trail it leaves glows brighter than most galaxies. As the black hole plows through interstellar gas, it compresses and heats the material, triggering bursts of star formation in its wake. Astronomers call this a light echo, and it's the only reason we can track this invisible monster at all. Without that glowing streak, we'd have no idea a billion solar mass black hole was sailing through the darkness. And here's the kicker. This isn't the only runaway. Another candidate, hyperluminous X-ray source XJ1417 plus 3257, might be an even larger black hole on the lam, zooming away at 4.7 million miles per hour. These rogue behemoths challenge everything we thought we knew about how black holes behave. They're not just anchors holding galaxies together, they're intergalactic wanderers rewriting the rules as they go. So where's 3C186 headed? At its current speed, it could cross the distance between Earth and the Moon in just 3 minutes. But don't worry, it's currently 2 billion light-years away, tearing through a lonely stretch of the cosmos. Its fate, to drift forever in the void, a king dethroned, its reign over a galaxy cut short by a gravitational twist of fate. But if you think that's an oddball, wait until you meet the black holes that spin so fast they turn space-time into a carnival mirror. What if everything we think we know about black holes is just an illusion, a cosmic sleight of hand? The holographic principle flips our understanding on its head, suggesting these monstrous voids might actually be two-dimensional projections, like a movie screen playing a 3D universe. Here's the mind-bending part. All the information about what falls into a black hole, every atom, every photon, even your favorite pair of socks if you dared to jump in, could be perfectly preserved on its surface, the event horizon. Not inside, not in some hidden core, but painted onto a 2D boundary like a cosmic barcode. This isn't some fringe idea. It's rooted in the work of physicists like Leonard Susskind and Gerard T. Hooft, who realized black holes obey a strange rule. The maximum entropy, or chaos inside any region of space, isn't determined by its volume, but by the area of its boundary. Think of it like a hard drive. A regular 3D hard drive stores data in its volume, but a black hole's hard drive is its surface. Every bit of information about what's inside gets smeared across the event horizon in tiny Planck-scale pixels, each no bigger than 1/10,000,000th of a billionth of a billionth of a centimeter. To wrap your head around this, picture a hologram sticker, shine light on it, and suddenly it pops into a 3D image, but tilt it sideways and you'll see it's just a flat, patterned surface. The holographic principle suggests black holes work the same way. Their immense gravity warps space-time so severely that the true reality, the complete data of everything they've swallowed, exists on a 2D surface, while the 3D interior is just a shadow. It's why Stephen Hawking's black hole information paradox sparked decades of debate. If information isn't lost but encoded on the horizon, then black holes aren't cosmic shredders. They're the universe's most secure filing cabinets, and here's where it gets wilder. This isn't just about black holes. It might be a clue to quantum gravity, the holy grail of physics. String theorists argue that if a black hole's interior can be described entirely by interactions on its surface, perhaps the entire universe could too. We might be living inside a higher dimensional projection with the cosmos's true blueprint written on some distant, invisible boundary. So next time you see an image of a black hole's swirling disk, remember, the real magic isn't in the darkness. It's on the edge where every falling star, every lost spacecraft, every atom is etched into the fabric of spacetime itself, a cosmic Rosetta Stone waiting to be decoded. And if physicists are right, unlocking its secrets could reveal that reality isn't what it seems. It's a hologram playing on the grandest screen imaginable. Black holes were long thought to be the ultimate bald objects in the universe, cosmic cue balls governed by the infamous no-hair theorem. This idea, coined by physicist John Wheeler, suggested that black holes could be described by just three simple traits: mass, spin, and charge. Everything else, the type of matter they swallowed, the stars they shredded, even the screaming piano we talked about earlier, would be permanently erased beyond the event horizon. But new research is flipping this notion on its head, revealing that black holes might actually grow hair, after all, not literal strands, but intricate patterns of magnetic fields and quantum effects clinging to their surfaces like cosmic static. The game-changing discovery came from simulations of black holes with extreme magnetic fields. When scientists modeled what happens to these fields as matter falls in, they found something astonishing. Instead of vanishing forever, the magnetic lines can get stuck on the event horizon, twisting into complex braids that ripple across the surface. It's like throwing a bundle of rubber bands into a fan. Some might get sliced apart, but others could tangle around the blades in unexpected ways. These magnetic hairs aren't just decorations. They subtly alter how the black hole interacts with its surroundings, leaving fingerprints that could theoretically be detected from Earth. And it's not just magnetism. Quantum mechanics adds another layer of fuzz. Virtual particles popping in and out of existence near the event horizon, the same phenomenon behind Hawking radiation, can imprint quantum hair on the black hole's surface. Think of it as a cosmic etch-a-sketch. Every time something falls in, the disturbance leaves a faint but permanent mark in the quantum foam clinging to the horizon. Recent calculations suggest these quantum hairs might even store information about what the black hole consumed, like a celestial hard drive encoding the history of everything it's ever eaten. This throws a wrench into the no-hair theorem's elegance. If confirmed, it means black holes aren't the simple, featureless pits we once thought. They're more like cosmic Russian nesting dolls with layers of complexity hidden just beneath the surface. The implications ripple across physics. If black holes can retain traces of what falls in, it could solve the information paradox once and for all, proving that not even the universe's hungriest monsters can truly erase the past. So next time you picture a black hole, don't imagine a smooth, dark sphere. Picture instead a turbulent, flickering surface etched with invisible strands. Each one a whisper of the chaos it's witnessed, a tangled ledger of everything it's stolen from the cosmos. And if we ever learn to read that ledger, we might finally crack the code of how reality itself stores its secrets. Imagine a black hole so colossal, it makes our entire galaxy look like a speck of dust in comparison. Meet TUN 618, the universe's most gargantuan black hole we've ever discovered, a behemoth tipping the scales at 66 billion times the mass of our Sun. To put that into perspective, that's more than the combined weight of every star in the Milky Way, squeezed into a single, unfathomable singularity. If placed at the center of our solar system, its event horizon would stretch past Pluto's orbit, swallowing planets like marbles. What makes TUN 618 truly mind-bending isn't just its size, but its appetite. This ultra-massive monster devours the equivalent of one sun every single day, fueling a quasar so luminous it outshines entire galaxies. Even from 12 billion light-years away, its brilliance pierces the cosmic darkness, visible to us only because its light has been traveling since the universe was a toddler. But here's the real kicker. TON 618 isn't just growing, it's breaking physics. Theorists once thought black holes couldn't exceed 50 billion solar masses, fearing their own radiation pressure would blast away nearby matter before they could grow larger. Yet TON 618 laughs at those limits. Its existence forces us to rethink how these cosmic titans form. Did it gorge on galaxies during the universe's chaotic youth? Or was it born already monstrous, a primordial giant from the dawn of time? And don't mistake TON 618 for a lone predator. It's the heart of a galaxy, its gravity orchestrating the motions of billions of stars. Yet even that galaxy is dwarfed by its black hole's shadow, a sobering reminder that sometimes the tail wags the dog. In a cosmos full of wonders, TON 618 stands as a humbling paradox, a void so vast it twists our understanding of scale itself. But size isn't its only secret. This black hole's accretion disk is a cosmic hurricane spinning at temperatures of millions of degrees. If you could stand near it and somehow survive, the skies would blaze with light 100,000 times brighter than our sun, a radiant hellscape wrapped around the darkest pit in existence. Astronomers call objects like TON 618 ultramassive for a reason. They defy the ordinary. And as we peer deeper into the universe's corners, who knows what even larger giants we might find. After all, the cosmos has a way of outdoing our wildest imaginations. When two neutron stars collide in a cataclysmic explosion called a kilonova, they don't just create a light show, they forge the universe's heaviest elements in a cosmic alchemy furnace. Gold, platinum, uranium, even the wedding ring on your finger might owe its existence to one of these violent mergers billions of years ago. But here's the twist. Black holes could be the unseen puppeteers behind these rare, glittering explosions, orchestrating the conditions for gold to reign across the cosmos. Take the historic kilonova GW 170817, detected in 2017. When the LIGO and Virgo gravitational wave observatories caught the ripples from this neutron star collision, astronomers witnessed something unprecedented. The birth of an entire solar system's worth of heavy elements in mere seconds. The process is mind-bending. As the neutron stars spiral toward each other, chunks of their ultra-dense matter get flung into space, forming a swirling, neutron-rich debris cloud. In this exotic environment, atomic nuclei are bombarded with neutrons so rapidly, a process called R-process nucleosynthesis. They balloon into heavy elements almost instantly. A single teaspoon of this neutron star material could weigh 1 billion tons, and when it decays, it literally transmutes into gold. But where do black holes come in? The universe has a dirty secret. Most neutron star mergers might not happen in isolation. Simulations suggest that in dense stellar environments like globular clusters, a third player, often a black hole, can destabilize neutron star pairs, hurling them toward collision. Picture two dancers spinning gracefully until a third crashes into them, sending one or both spiraling out of control. Black holes don't just provoke these crashes, they can also consume one neutron star mid-collision, creating a bizarre hybrid event where gold production and a black hole birth happen simultaneously. And the aftermath, pure cosmic spectacle. The newly formed black hole, now surrounded by a debris disk of neutron-rich material, can launch jets of matter at near light speed, lacing entire galaxies with precious metals. Some theories even suggest that most of the universe's gold might come from these black hole-triggered mergers, not solo neutron star collisions. That's right, the gold in your jewelry might have been forged in the accretion disk of a newborn black hole, then blasted across space like cosmic shrapnel. So next time you hold a gold coin, remember, its atoms were likely born in one of the universe's most extreme events, possibly orchestrated by the very thing we thought only destroyed black holes. They're not just cosmic wrecking balls, they're the unseen goldsmiths of the cosmos, turning the ashes of dead stars into treasures that outlive galaxies. And if that doesn't make you rethink their role in the universe, consider this. The next kilonova could be brewing right now in some distant cluster with a black hole pulling the strings. When it detonates, it'll sow the seeds of future civilizations, literally gilding the cosmos one collision at a time. Most black holes announce their presence with a blazing signature, superheated gas swirling into an accretion disk glowing brighter than a billion suns. But what about the ones that don't? Imagine a black hole so stealthy it doesn't shred stars or gulp down gas clouds. No X-ray screams, no fiery jets, just pure, perfect darkness. These cosmic phantoms exist, and they're hiding in plain sight, invisible to traditional telescopes. Yet astronomers have a trick up their sleeves to unmask them: gravitational lensing, nature's ultimate flashlight for the darkest corners of space. Here's how it works. When a massive object like a black hole drifts between us and a distant star, its gravity bends the fabric of space-time, acting like a cosmic magnifying glass. The star's light warps around the black hole, creating a telltale distortion, a sudden brightening or splitting of the star's image. It's like spotting a hidden object by the way it bends the air above a hot road. No accretion disk needed. The black hole betrays itself by its gravitational fingerprint alone. In 2018, astronomers hunting these invisible predators got their first confirmed catch. A team monitoring millions of stars in the galaxy's bulge spotted one that flared mysteriously, its light intensifying for months before fading. The culprit: a rogue black hole at least 4 times the mass of our Sun, drifting silently through interstellar space. No X-rays, no glowing disk, just the subtle stretch of starlight around its event horizon, a ghost caught in the act. But the real kicker: these dark wanderers might outnumber their glowing cousins. For every supermassive black hole blazing at a galaxy's heart, there could be thousands of stellar mass, dark black holes lurking undetected between the stars. Some might even be primordial black holes born in the Big Bang's first moments, too small to attract gas but massive enough to lens light. They're the universe's best hide-and-seek players, and gravitational lensing is the only way to call them out. So next time you look up at the night sky, remember, what you don't see might be just as fascinating as what you do. The darkness isn't empty, it's threaded with invisible giants, bending light and rewriting the rules of detection. And with every lensed star we find, we're one step closer to mapping the cosmos's hidden architecture, one ghostly black hole at a time. Black holes might be more than cosmic vacuum cleaners. Some scientists suspect they could be shortcuts through spacetime itself. The idea isn't just ripped from sci-fi, it's rooted in Einstein's equations. Back in 1935, Albert Einstein and Nathan Rosen theorized that the extreme curvature of spacetime near a black hole's singularity might connect to another point in the universe, or even another universe entirely. They called it an Einstein-Rosen bridge, but you probably know it by its catchier nickname, a wormhole. Picture a sheet of paper folded in half. Now poke a pencil through both layers. The pencil's path is your wormhole, a tunnel cutting through the fabric of spacetime, turning a billion light-year journey into a stroll across the gap. In theory, a black hole's crushing gravity could create one end of this tunnel, while its hypothetical opposite, a white hole, spews everything out the other side. There's just one catch: traversing it would require surviving forces so brutal they'd turn you into a stream of atoms long before you reached the exit. But don't lose hope just yet. Quantum physics offers a wilder twist. At the tiniest scales, spacetime isn't smooth. It's a frothing sea of virtual particles popping in and out of existence, what physicists call quantum foam. Some theories suggest these microscopic bubbles could contain fleeting wormholes, constantly forming and collapsing. Under the right conditions, maybe, just maybe, one could be stabilized. How? Imagine flooding a tunnel with exotic matter, a hypothetical substance with negative energy that could prop the wormhole open like cosmic scaffolding. Sci-fi loves this idea, from Interstellar's Gargantua to Stargate's iconic rings, but reality might be stranger. If traversable wormholes exist, they could defy time itself. Step in one end, and you might emerge not just somewhere else, but someone else. The catch: exotic matter hasn't been found, and quantum foam wormholes would be smaller than atoms. Yet the math doesn't rule them out, and in a universe where black holes twist reality into knots, who's to say what's impossible? Here's the kicker: even if wormholes are purely theoretical, they've reshaped how we see black holes. They're no longer just endpoints, they're cosmic question marks. Maybe they're destroyers, maybe they're backdoors, or maybe they're something we haven't even dreamed of yet. One thing's certain: the deeper we look, the less we truly know. For centuries, black holes existed only in equations until April 10, 2019, when humanity finally stared one in the face. The now iconic image of Messier 87's supermassive black hole, resembling a fiery donut floating in the void, was more than just a scientific triumph. It was the culmination of a near-impossible feat requiring 8 radio telescopes across 4 continents to transform Earth itself into a planet-sized camera. The Event Horizon Telescope collaboration didn't just push boundaries, it rewrote them. To capture something as tiny as a black hole's shadow from 55 million light-years away, astronomers needed resolution 10,000 times sharper than the Hubble Space Telescope. That's like spotting a bagel on the moon from your backyard, but Earth's atmosphere blurs radio waves, so no single dish could do the job. The solution: synchronized telescopes from Hawaii to Spain to Antarctica, using atomic clocks precise to within 1 second every 100 million years, all staring at M87 simultaneously for 10 nights straight. The data collected, a staggering 5 petabytes, enough to store every selfie ever taken by every human who's ever lived. Then came the real challenge: stitching together this mountain of data. For 2 years, supercomputers combed through the observations, filtering out interference from atmospheric water vapor and even the Milky Way's own radio noise. The team essentially had to unscramble a cosmic jigsaw puzzle without knowing what the final picture should look like. When the glowing ring finally emerged, proof of light bending around the event horizon, it confirmed Einstein's century-old predictions down to the pixel. But here's what makes this image miraculous: we weren't seeing the black hole itself. That's impossible. What the HT captured was the silhouette of its event horizon, the point where light surrenders to gravity, wreathed in superheated plasma spinning at nearly light speed. The asymmetry in the ring's brightness, that's relativistic beaming, where light on the side spinning toward us appears brighter due to mind-bending time dilation effects. Every detail in that orange glow is a physics textbook come to life. This wasn't just a photo. It was humanity's first direct evidence that black holes aren't theoretical ghosts, they're real, dynamic monsters shaping the cosmos. And the HT is just getting started. With new telescopes joining the array, future images could reveal how black holes change over time, or even capture Sagittarius, a star in motion. What began as a fuzzy ring may soon become a high-definition movie of spacetime itself crumpling like paper. Not bad for a species that only learned to write 5,000 years ago. Black holes might seem eternal, cosmic traps where nothing ever escapes, but even these gravitational titans have an expiration date. Thanks to Stephen Hawking's groundbreaking work in the 1970s, we now know black holes can slowly evaporate, vanishing in a final burst of energy so strange it defies everything we thought we knew about gravity. This process, called Hawking radiation, reveals that black holes aren't just eaters, they're cosmic ice cubes melting away in the dark over unimaginable timescales. Here's how it works. Quantum mechanics tells us empty space isn't really empty, it's a seething foam of virtual particles, constantly popping in and out of existence. Normally, these particle pairs annihilate each other instantly, but at the edge of a black hole's event horizon, something bizarre happens. If one particle falls in while the other escapes, the black hole effectively loses a tiny bit of mass. Over time, this slow leak adds up. The smaller the black hole, the faster it evaporates, shrinking like a snowball in the sun until pop, it vanishes in a flash of gamma rays. Picture a black hole the mass of a small asteroid. According to Hawking's calculations, it would radiate away its entire existence in less than a second, exploding with the energy of 1,000,000 hydrogen bombs. But a typical stellar mass black hole, that would take longer than the current age of the universe to evaporate, around 10 to the 67 years, a number so vast it dwarfs all of cosmic history. And supermassive black holes like Sagittarius A, they'd need 10 to the 100 years to fade, a time span that makes eternity look like a blink. What's truly mind-bending is what happens in those final moments. As the black hole nears its end, its temperature skyrockets, emitting particles at an ever-increasing rate. In its last second, it could release as much energy as all the stars in the observable universe combined, a cosmic mic drop written in gamma rays. Some theorists even speculate these final explosions might leave behind exotic relics like Planck mass remnants or even rips in spacetime itself. Hawking radiation isn't just a theoretical curiosity, it's a revolution. It bridges quantum mechanics and gravity, two fundamental forces that have stubbornly resisted unification. And if we ever detect the telltale signature of a dying black hole, a sudden, high-energy burst with no visible source, it would be one of the greatest validations of theoretical physics in history. So while black holes may rule the cosmos today, they're not invincible. Given enough time, even the darkest giants flicker out, their legacies etched not in matter but in the fleeting glow of their final farewell. But here's the twist. Hawking's discovery also implies that black holes aren't the perfect prisons we once thought. Information swallowed by a black hole might not be lost forever. It could slowly leak back out, scrambled into Hawking radiation like a cosmic game of telephone. That's a story for another time, but one thing's certain. In the grand tale of the universe, even black holes are just temporary actors on an infinite stage. Black holes don't just swallow light, they bend it into impossible shapes, turning the cosmos into a funhouse mirror. This bizarre phenomenon, called gravitational lensing, is one of Einstein's most dramatic predictions in action. Picture a marble rolling across a stretched rubber sheet. The dent it creates warps the path of anything passing nearby. Now replace the marble with a black hole and the rubber sheet with spacetime itself, and you've got a cosmic illusion so striking it can make one distant object appear as four. Take the famous Einstein cross, a quasar 500 million light-years away that's been multiplied into a perfect celestial X by the gravity of an entire galaxy. The supermassive black hole at that galaxy's heart curves spacetime so severely, it splits the quasar's light into mirrored copies, each a ghostly echo of the original. From Earth, we see not one glowing beacon, but four arranged around the lensing galaxy like points on a compass. It's as if the universe itself is playing a trick on our eyes, proving that even light can't travel in a straight line when a black hole's gravity gets involved. But the real magic happens when you zoom in on the details. Each of those four quasar images isn't just a carbon copy, they flicker out of sync. That's because the light forming each image takes a slightly different path around the galaxy, with some rays detouring longer than others. It's like watching the same scene through four different security cameras, each with its own delay. Astronomers have used this time lag effect to measure cosmic distances with precision, turning gravitational lensing into a tape measure for the universe. And sometimes the funhouse mirror gets even weirder. When a black hole aligns perfectly with a background star, it can stretch the star's light into a glowing ring, an Einstein ring where the entire sky gets warped into a halo. In rare cases like the galaxy S002315, this ring becomes so distorted, it looks like a smeared fingerprint on the cosmos. These aren't just pretty pictures, they're snapshots of spacetime itself twisting under the weight of unseen giants. What's truly staggering, this isn't some rare cosmic fluke. Hubble has spotted hundreds of these lensed quasars and rings, each one a testament to how black holes don't just hide in the dark. They sculpt the light around them into surreal art. And with every new observation, we're reminded the universe doesn't just have black holes, it dances with them, bending to their gravity in ways we're only beginning to decode. So next time you see a multiple image quasar or a warped Einstein ring, remember, you're not just looking at a trick of the light. You're seeing spacetime itself fold under the weight of the universe's most enigmatic architects, proving once again that reality is stranger and more beautiful than we ever imagined. We might think of black holes as distant cosmic monsters lurking in the far reaches of space, but what if one was practically in our stellar backyard? Meet HR 6819, a silent predator hiding just 1,000 light-years from Earth, making it the closest known black hole to our solar system. To put that in perspective, if the Milky Way were the size of a football field, this black hole would be lurking just 10 yards away. And here's the twist, we wouldn't even know it existed if not for two stars behaving like they were being tugged by an invisible leash. The discovery reads like a celestial detective story. Astronomers were studying HR 6819, a seemingly ordinary star system in the constellation Telescopium, when they noticed something peculiar. The system's inner star was orbiting nothing at breakneck speeds, completing a full loop every 40 days, while an outer star circled much farther away. That frantic dance could only mean one thing: an unseen, massive object was yanking the inner star around. After crunching the numbers, the verdict was undeniable. Hidden in the void between those stars was a black hole roughly 4 times the mass of our Sun, its gravity warping their motions like a puppeteer pulling strings. But here's what makes HR 6819 so bizarre: it's invisible. Unlike most black holes that reveal themselves by shredding nearby stars or glowing with X-rays, this one is dormant, a cosmic recluse drifting quietly through space. Without those telltale stellar wobbles, we'd have no clue it was there. It's the ultimate stealth assassin, proving that black holes don't always announce their presence with cosmic fireworks. This discovery rewrote the map of our cosmic neighborhood. Before HR 6819, the closest known black hole was roughly 3,000 light-years away. Now, astronomers suspect there could be hundreds more lurking even closer, camouflaged in plain sight among the stars we see every night. Imagine looking up at the constellation Orion and realizing one of those familiar pinpricks of light might actually be a binary system hiding a dark secret. And the implications are staggering. If dormant black holes really are this common, they could be the universe's silent majority. Black holes that don't feed, don't glow, and don't give away their presence unless a star happens to orbit them just right. It's like realizing your quiet next-door neighbor has been a secret agent all along. But HR 6819 isn't just a curiosity, it's a golden opportunity. Because it's so close and so calm, astronomers can study it in unprecedented detail, testing theories about how black holes form and evolve without the chaos of an active accretion disk. It's the perfect cosmic lab right on our galactic doorstep, so next time you gaze at the night sky, remember, the darkness between the stars might not be as empty as it seems. There could be invisible giants watching from the shadows, their presence betrayed only by the subtle sway of the stars they haunt. And if one black hole slipped under our radar until now, who knows what else might be hiding in the quiet corners of the cosmos? Black holes don't just lurk in the darkness sometimes, they crash together in the most violent mergers the universe has ever seen. And when they do, they don't just collide, they sing. Or more accurately, they let out a cosmic chirp, a fleeting ripple in space-time so precise, it sounds like a bird calling from the void. This isn't science fiction. It's gravitational wave music, captured for the first time in 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory, and it changed astronomy forever. The sound of two black holes colliding is nothing like the explosive crashes you'd expect. Instead, it's a rapid, high-pitched chirp that rises in frequency before abruptly cutting off. That's the moment the two black holes, each dozens of times heavier than our sun, spiral into each other at nearly the speed of light, merging into a single, more massive monster. The whoop you hear is the literal sound of space-time itself ringing like a bell, with gravitational waves stretching and squeezing everything in their path, including the atoms in your body. Here's what makes this chirp so extraordinary. Before LIGO, black holes were silent assassins, detectable only if they were actively devouring something. But gravitational waves predicted by Einstein a century ago, let us hear them even in total darkness. The merger LIGO caught, dubbed GW150914, came from two black holes over 1 billion light-years away. One weighed 36 solar masses, the other 29. As they danced closer, their gravitational waves grew louder, spiraling faster until blip. They became 158 solar mass black hole in a fraction of a second. The energy released, 3 solar masses converted into pure gravitational waves, briefly outshining every star in the observable universe combined. But the real magic lies in how we caught it. LIGO detectors are essentially giant cosmic microphones. Twin facilities in Washington and Louisiana shoot laser beams down 4-kilometer-long vacuum tubes measuring tiny distortions when a gravitational wave passes. We're talking changes 1,000 times smaller than a proton. That's like measuring the distance to Alpha Centauri with an accuracy of 1 human hair. When the wave from GW150914 hit, it stretched one arm of LIGO while squeezing the other, creating an interference pattern that scientists translated into sound. This wasn't just a one-time event. Since 2015, LIGO and its European counterpart, Virgo, have detected dozens of these mergers, some between black holes, others between neutron stars, and even a few bizarre pairings of both. Each chirp is a unique fingerprint, revealing the masses, spins, and distances of the colliding objects. The implications are staggering. Gravitational wave astronomy lets us study black holes no light could ever escape from, piercing the darkness like never before. Some mergers defy expectations, like GW190521, a collision so massive it shouldn't exist under current theories. Others, like GW170817, came with a fireworks show of gamma rays and gold, proving neutron-star mergers forge heavy elements. So next time you hear that cosmic chirp, remember, you're not just listening to black holes colliding. You're hearing the universe itself vibrate, a whisper from the darkest corners of reality telling stories no telescope could ever see. And with every new detection, the chorus grows louder, revealing a universe far wilder and far more musical than we ever dreamed. Here's something that defies all intuition. Black holes aren't just cold voids, they radiate heat. That's right, these cosmic monsters have temperature, a discovery so shocking it rewrote the laws of physics. In the 1970s, Jacob Bekenstein and Stephen Hawking revealed a truth that still boggles the mind: black holes glow. Not with light, but with an eerie quantum whisper called Hawking radiation. And the formula they derived, the Bekenstein-Hawking equation, holds the key to one of the universe's strangest paradoxes. The bigger the black hole, the colder it gets. Picture an ice cube floating in space. The warmer the surroundings, the faster it melts. But black holes flip this logic on its head. A stellar mass black hole might have a temperature of just 1/1,000,000th of a degree above absolute zero. Colder than the cosmic microwave background, the faint afterglow of the Big Bang itself. Meanwhile, a supermassive behemoth like Sagittarius A, it's practically freezing, chilling at a bone-numbing 10 to the minus 14 Kelvin. That's colder than the emptiest voids between galaxies. How does this work? Hawking's breakthrough tied quantum mechanics to gravity in a way no one expected. At the event horizon, quantum fluctuations create pairs of virtual particles. Normally, they'd annihilate instantly, but when one falls into the black hole while the other escapes, the black hole loses energy, shrinking over time. The temperature of this radiation depends on the black hole's surface gravity, which bizarrely decreases as the black hole grows. It's like a campfire. A roaring blaze feels hot up close, but a bonfire the size of a mountain would barely warm your hands. Here's the kicker. This means black holes evaporate, given enough time, and we're talking timescales so vast, the universe itself would fade to black first. Even the mightiest black hole would dissolve into a final burst of particles. A grapefruit-sized primordial black hole, it'd explode in a blaze of gamma rays today, but ton 618, that 66 billion solar mass titan. It'll outlast every star, every galaxy, even the last flickers of light in the cosmos. The irony is delicious. Black holes, the ultimate symbols of cosmic destruction, are slowly leaking themselves into oblivion, not with a scream but with a quantum sigh. And somewhere in that faint glow lies the answer to one of physics' biggest puzzles. What happens to all the information they swallow? But that's a mystery hot enough to melt even the coldest black hole's icy reputation. What if our entire universe isn't just floating in space, but is actually inside another universe's black hole? This isn't some trippy thought experiment. It's a legitimate scientific hypothesis called cosmological natural selection, and it flips the script on everything we assume about reality. The theory, championed by physicist Lee Smolin, suggests that black holes don't just destroy, they create. Every time a black hole forms in one universe, it could be birthing an entirely new cosmos in its depths with slightly tweaked physical laws. That means the Big Bang might not have been the beginning, just another link in an infinite chain of universes, each spawning from the collapse of a black hole in a parent universe. Here's how it works. When matter gets crushed into a singularity, the extreme conditions might trigger a quantum rebound, a sort of cosmic reset button. Instead of collapsing into infinite density, the singularity could explode outward, creating a new spacetime bubble with its own unique physics. Think of it like a seed sprouting inside a fruit. The black hole's interior becomes fertile ground for a new universe, inheriting some traits from its parent while mutating others. Over cosmic timescales, universes that produce more black holes would reproduce more often, leading to a multiverse where the laws of physics favor black hole formation. It's evolution, but on a scale so vast it makes Darwin's theories look quaint. The implications are staggering. If true, our universe's finely tuned constants, the strength of gravity, the mass of an electron, might not be random. They could be the result of countless generations of cosmic trial and error, optimized for one thing, making more black holes. Even the Big Bang's near-perfect uniformity, the so-called horizon problem, could be explained. The infant universe wasn't smooth because of inflation. It was smooth because it inherited orderly conditions from the black hole that birthed it. Critics argue this theory is untestable, but Smolin disagrees. If cosmological natural selection is real, universes should evolve to maximize black hole production. That means certain physical parameters like the mass of neutrons or the curvature of spacetime should cluster around values that favor stellar collapse. Some physicists even suggest looking for anti-tuned universes in quantum fluctuations as potential evidence of this evolutionary process, the wildest part. This isn't the only hypothesis suggesting black holes are cosmic parents. Some interpretations of string theory propose that our universe could be a holographic projection from a 2D surface surrounding a black hole in a higher dimensional space. Others speculate that white holes, the theoretical opposites of black holes, might be the Big Bangs of other universes, spewing out matter that collapsed elsewhere. So next time you gaze at the night sky, consider this. The darkness might not be an empty void, but a nesting doll of realities, each hidden inside the belly of a black hole we'll never see. And if Smolin is right, black holes aren't the end of the story. They're just the beginning of someone else's. Black holes don't just swallow matter, they might erase the very history of the universe. This terrifying idea struck Stephen Hawking in the 1970s, igniting a decades-long battle between two pillars of physics, quantum mechanics and Einstein's relativity. The problem: quantum theory says information, the fundamental blueprint of every particle's past, can never be truly destroyed. But black holes, with their inescapable event horizons, seem to violate this sacred rule, devouring stars, planets, and even light without leaving a trace of what they once were. Hawking's bombshell conclusion: black holes aren't just cosmic trash compactors, they're universe-scale shredders, permanently deleting information from existence. The physics world erupted. If Hawking was right, it meant rewriting quantum theory itself. Enter Leonard Susskind, who famously declared this idea utterly repugnant and launched a counterattack. The crux of his argument, holography: Susskind and Dutch physicist Gerard T. Hooft proposed that every particle swallowed by a black hole leaves a two-dimensional imprint on its event horizon, like a shadow cast on a cave wall. The information isn't lost, it's scrambled into an indecipherable quantum code, preserved in the surface area of the black hole rather than its volume. It's as if the universe keeps backup files, just in an alien format we can't yet read. Hawking himself eventually conceded, but the debate reshaped physics forever. The resolution, dubbed black hole complementarity, suggests both theories might be right depending on your perspective. For an outside observer, information smears across the horizon like cosmic graffiti, never truly vanishing. But for someone foolish enough to dive in, from their doomed viewpoint, everything hits the singularity and winks out. It's a cosmic sleight of hand where reality itself has multiple versions, each valid but irreconcilable. This paradox still isn't fully solved. Some theorists, like Juan Maldacena, argue black holes are holograms projecting a three-dimensional illusion from a two-dimensional surface, an idea that's inspired radical new models of the universe itself. Others, like Roger Penrose, suggest lost information might escape via Hawking radiation, encoded in subtle quantum correlations. The wildest twist: if information can escape, it implies black holes have memories, traces of everything they've consumed lingering like ghosts in their evaporating glow. What's at stake isn't just academic. If black holes really destroy information, it undermines quantum mechanics' ability to predict the future, the very foundation of reality's predictability. But if they preserve it, hidden in some quantum vault we can't yet access, it hints at a universe far stranger and more interconnected than we ever imagined. Either way, these gravitational monsters aren't just testing our theories, they're forcing us to rewrite them. Most stars spend their lives in predictable orbits, dancing around galactic centers or paired with other stars in gentle gravitational embraces. But LB1 is different. This massive blue star isn't circling another star or drifting peacefully through space. It's locked in a cosmic tango with something far stranger, a black hole so unexpectedly massive, it defies everything we thought we knew about how these systems form. Astronomers call it a quiet black hole, no glowing accretion disk, no violent outbursts, just the silent, invisible tug of gravity dictating every move LB1 makes. The discovery sent shockwaves through astrophysics. LB1's black hole companion weighs in at a staggering 70 times the mass of our Sun. That's not just big, it's impossibly big, at least according to traditional models of stellar evolution. Conventional wisdom says black holes this size shouldn't exist in our galaxy. When massive stars die, their violent supernova explosions are supposed to blow away enough material to leave behind black holes no heavier than 20 solar masses. Yet here's LB1 casually orbiting a gravitational giant that shouldn't be there, like a planet orbiting a phantom sun. How did this cosmic oddball come to exist? One theory suggests the black hole might have formed differently, not from a single exploding star, but from the direct collapse of an ultra-massive star, skipping the supernova stage entirely. Picture a star so heavy and unstable, it doesn't even explode when it dies. Instead, it implodes silently, like a building collapsing inward without a sound, leaving behind a black hole far larger than any supernova could produce. Another possibility: this black hole might be the product of an ancient merger, two smaller black holes spiraling together long before LB1 entered the picture, their combined mass rewriting the rules of the system. But the real puzzle is LB1 itself. Stars this massive usually live fast and die young, burning through their fuel in just a few million years. Yet LB1 appears relatively pristine, untouched by the violent forces that should have ripped it apart or stripped its outer layers. It's as if the star and its dark companion have coexisted peacefully for eons, defying every expectation. This cosmic duo isn't alone. Other systems, like the recently discovered Gaia BH1, show similar mismatched partnerships, stars orbiting black holes they seemingly shouldn't survive near. Each discovery chips away at the old models, forcing astronomers to reconsider how black holes form, grow, and interact with their stellar neighbors. So next time you look up at the night sky, remember, the universe has a habit of breaking its own rules, and somewhere out there, LB1 and its unlikely partner are waltzing through the void, whispering secrets we're only beginning to decode. Black holes are defined by their event horizons, the ultimate point of no return where gravity wins forever. But what if that boundary didn't exist? Imagine a singularity floating bare in space, its crushing gravity exposed to the universe like an open wound. These hypothetical monsters are called naked singularities, and they defy everything we think we know about cosmic decorum. According to general relativity, they shouldn't exist. Yet the math doesn't outright forbid them, sparking a decades-long debate that's torn physicists apart. At the heart of the controversy is the cosmic censorship hypothesis proposed by Roger Penrose in the 1960s. It's essentially the universe's dress code: no singularities allowed without the modest covering of an event horizon. Penrose argued that nature abhors a naked singularity just as much as it abhors a vacuum, preventing these gravitational exhibitionists from forming in the first place. Why? Because without an event horizon, the infinite density of a singularity would be visible and, worse, touchable. The laws of physics as we know them would break down in plain sight, rendering causality and predictability impossible. Picture a calculator dividing by zero. Now imagine that glitch warping reality itself. But here's where it gets messy. While Einstein's equations suggest naked singularities could form under extreme conditions, like the collapse of a rapidly spinning star or the merger of two black holes, no one's ever seen one. Simulations show that certain configurations might momentarily expose a singularity before an event horizon snaps into place, like a cosmic curtain closing at the last second. It's as if the universe has a failsafe, a gravitational modesty screen ensuring singularities stay hidden. Yet some theorists, like the late physicist Joseph Polchinski, wondered if quantum effects might tear that curtain open. In hypothetical scenarios involving charged or rapidly rotating black holes, the event horizon could theoretically vanish, leaving the singularity bare. The implications are staggering. A naked singularity wouldn't just defy gravity, it could spit out unpredictable bursts of energy, warp space-time in ways we can't model, or even serve as a portal to, well, who knows. The very idea makes physicists shudder because without an event horizon, the universe loses its rulebook. For now, cosmic censorship holds firm. Every black hole we've observed behaves politely, keeping its singularity veiled. But the hunt for rebels continues. Some researchers scour gravitational wave data for anomalies that might hint at a naked singularity's fingerprint. Others simulate exotic matter to see if quantum mechanics might conspire to undress a black hole. If one were ever found, it wouldn't just rewrite textbooks, it would force us to admit that the universe has a wild side where even the most sacred laws are optional. Until then, naked singularities remain the ultimate cosmic taboo, thrilling, terrifying, and utterly forbidden. But if you think that's unsettling, wait until you hear about the black holes that might be older than time itself. Black holes don't just lurk at the centers of galaxies, they build them. Far from being cosmic wrecking balls, supermassive black holes like the one in Andromeda act as galactic architects, using unimaginable forces to sculpt star formation and dictate the fate of entire galaxies. Take Andromeda, our closest galactic neighbor. Its supermassive black hole, while seemingly dormant now, has spent billions of years unleashing cycles of creation and destruction through quasars and relativistic jets. These aren't random outbursts, they're a carefully balanced feedback system where the black hole's fury can either ignite star nurseries or snuff them out like a cosmic fire hose. When a black hole feeds, it doesn't just quietly swallow matter, it triggers a chain reaction. Gas and dust spiral into the accretion disk, heating up to millions of degrees until they blaze brighter than all the stars in the galaxy combined. This is a quasar, nature's ultimate particle accelerator. But here's the twist, that energy doesn't just vanish into the void. The black hole funnels some of it into jets, twin beams of plasma screaming outward at nearly light speed, punching through interstellar gas for thousands of light years. In Andromeda's younger days, these jets likely plowed through its core, compressing gas clouds in their wake and triggering waves of star birth. Astronomers call this positive feedback, where the black hole's tantrum ironically seeds new stars. But there's a flip side. Those same jets can also quench star formation by blasting away the raw materials stars need to form. Picture a gardener who both plants seeds and uproots sprouts. Supermassive black holes toggle between these roles like cosmic switches. In Andromeda, computer simulations suggest its central black hole went through periods of intense activity, flaring up as a quasar every few 100 million years. Each outburst heated surrounding gas to such extreme temperatures that it couldn't cool and collapse into new stars, effectively putting stellar production on pause. This push and pull explains why galaxies like Andromeda have dead zones near their cores, vast regions where stars are mysteriously scarce. The black hole's ancient outburst sterilized these areas, leaving behind a fossil record of its past violence. Yet farther out, its influence wanes, allowing spiral arms to bloom with young blue stars. It's a delicate equilibrium, too much black hole activity and the galaxy starves, too little and it drowns in unbridled starbirth. Modern telescopes have caught other galaxies in the act. The Whirlpool Galaxy's black hole, for instance, is currently firing jets that compress nearby hydrogen clouds, sparking pockets of star formation like fireworks along their path. Meanwhile, in galaxy cluster MS-735, jets from a central black hole have carved out cavities in intergalactic gas so vast they could swallow our entire Milky Way. These observations confirm that black holes don't merely inhabit galaxies, they engineer them, balancing cosmic scales with forces beyond human comprehension. Andromeda's quiet phase today is just an intermission. In a few billion years, as it merges with our Milky Way, its black hole will awaken again, feasting on fresh gas and reigniting the cycle. When it does, it won't just be a collision of stars and dust, it'll be a battle of titanic forces, where the unseen gravitational maestro in the center once again takes up its baton to conduct the next movement in the symphony of the cosmos. The event horizon of a black hole isn't always a death sentence. If you pick the right one, you might just survive long enough to witness the unthinkable. Most black holes would rip you apart before you even cross the threshold, stretching your body into a strand of atoms in a process called spaghettification. But supermassive black holes, like the one at the heart of our galaxy, are different. Their event horizons are so vast, stretching millions of kilometers, that the tidal forces near the boundary are surprisingly gentle. Step across the edge of Sagittarius A star and you wouldn't even feel it at first. You'd have minutes, maybe even hours, before the inexorable pull of gravity crushed you into the singularity. Picture this: you're descending toward a black hole the size of our solar system. The closer you get, the more the universe outside warps into a shrinking circle of light behind you, blue shifted into a blinding halo. Time slows to a crawl. A single minute for you could be years for someone watching from afar. But here's the twist: inside the event horizon, space itself is falling faster than light. There's no going back, but for a fleeting moment, you're not just a passenger, you're an explorer in the most forbidden territory in existence. What would you see? Simulations suggest the black hole's interior isn't pure darkness. Light from the accretion disk, the superheated ring of doomed matter outside, would bend inward, creating eerie, shifting patterns on the walls of your cosmic tomb. Some theories even propose that the singularity isn't a point, but a turbulent, corky horizon, where time and space swap roles. Here, the past might unravel around you like a film played backward, while the future collapses into a single, inescapable moment. Of course, surviving is relative. Eventually, the tidal forces, no matter how weak, would pull your body into a stream of particles spiraling toward the center. But in those final moments, you'd witness physics at its most extreme. Quantum effects, normally invisible, might flare into view as space-time itself fractures. Some models suggest you'd even hit the singularity not as a corpse, but as a wave of probability, your very atoms smeared across the fabric of reality. The craziest part: we may already have clues about what happens inside. Hawking radiation implies that black holes aren't perfect prisons. Information about what falls in might leak back out, scrambled into quantum noise. If true, your journey into the abyss could leave faint echoes in the universe, a ghostly signature of your final moments. So while no one's volunteering to test this theory, it's a haunting reminder. Even in the universe's darkest corners, the rules are stranger than we dare imagine. When two black holes collide and merge, the violence of their union doesn't end with the final crash. It sets off an otherworldly reverberation, a cosmic echo that shakes the fabric of space-time itself. This fleeting but explosive aftermath is called the ring-down phase, and it's the universe's version of striking a bell and listening to the lingering hum. Except in this case, the bell is a newborn black hole, and the sound is gravitational waves rippling outward at the speed of light, carrying secrets about the most extreme event in the cosmos. Imagine tossing a pebble into a still pond. The initial splash is like the moment the black holes merge, a chaotic burst of energy. But what follows is just as important: the concentric ripples spreading outward, slowly fading as the water settles. In black hole mergers, those ripples aren't made of water. They're distortions in space-time, a symphony of vibrations revealing the newborn black hole's mass, spin, and even its shape. Scientists liken this to tapping a wine glass and listening to its pitch to determine how much liquid is inside. Only here, the pitch is a gravitational wave signal, and the glass is an object so dense it defies ordinary physics. The ring-down phase is shockingly brief, often lasting just milliseconds, but within that blink of an eye, the newly formed black hole settles into its final state, shedding imperfections like a spinning top wobbling before finding its balance. The gravitational waves emitted during this phase aren't random. They follow precise mathematical patterns called quasi-normal modes. These are the space-time equivalent of musical notes, each one corresponding to how the black hole's surface vibrates as it stabilizes. The louder the note, the more dramatic the distortion, the higher the frequency, the more compact the black hole. Detecting these vibrations isn't just a curiosity, it's a groundbreaking test of Einstein's theory. In 2015, when LIGO caught its first black hole merger, the ring-down phase was the smoking gun confirming the final product was indeed a black hole and not some exotic cosmic imposter. The signal matched predictions down to the finest details, a triumph for general relativity. But there's a twist. Some physicists speculate that if deviations from Einstein's equations ever appear, they'll likely show up in the ringdown. Tiny anomalies in the gravitational wave notes could hint at new physics, perhaps evidence of extra dimensions, quantum gravity effects, or even exotic objects like wormholes. The wildest part, this cosmic ringing isn't just a one-time event. Every black hole merger in the universe, from the earliest epochs to collisions happening right now in distant galaxies, triggers its own unique ringdown. Future observatories like the space-based LISA mission could detect these echoes from mergers so ancient they occurred before the first stars formed. Each one is a time capsule, a snapshot of space-time pushed to its limits. And as our detectors grow more sensitive, we're not just listening to black holes collide, we're tuning in to the universe's hidden soundtrack, one gravitational chime at a time. Forget fighter jets or speeding asteroids. The fastest objects in the universe aren't just propelled by explosions or gravity slingshots. They're hurled into the void by black holes playing a game of cosmic pinball. Meet hypervelocity stars blazing through space at speeds up to 1.6 million miles per hour. So fast, they're not just escaping their home galaxies, they're breaking free from the gravitational grip of galactic clusters entirely. And the launchers behind these interstellar bullets, binary black holes where two monsters orbiting each other turn stars into celestial cannonballs. Here's how this intergalactic fastball works. Imagine a star drifting too close to a pair of black holes locked in a gravitational dance. As it approaches, one black hole grabs it, slingshots it around, and then, like a catapult releasing its payload, flings it toward the second black hole. The second black hole then adds its own gravitational kick, accelerating the star to unimaginable speeds. This isn't just a gentle nudge, it's a full-scale launch, with the star's velocity surpassing even the escape velocity of the Milky Way. The energy involved is staggering, equivalent to detonating 1 million nuclear bombs in perfect unison. The first hypervelocity star, dubbed S5HVS1, was discovered in 2005, racing away from the Milky Way at 1.7 million miles per hour. Since then, astronomers have spotted dozens more, each one a runaway rebel with a trajectory tracing back to the galactic core, where supermassive black holes lurk. But here's the twist: not all hypervelocity stars come from binaries. Some might be survivors of disrupted dwarf galaxies, or even rogue stars flung outward by supernova explosions. Yet the fastest, the ones defying all odds, almost always point to binary black hole interactions as their origin story. What happens to these stellar speed demons? They don't just vanish into the dark. As they barrel through intergalactic space, they leave glowing trails of ionized gas, cosmic breadcrumbs marking their paths. Some might eventually collide with other galaxies, while others are doomed to drift forever in the void, freezing into stellar icebergs over billions of years. But their real value isn't in their fate, it's in their origins. By studying hypervelocity stars, astronomers can map the hidden dynamics of black hole binaries, revealing how these gravitational powerhouses shape galaxies from the inside out. And the record breaker, a star named Almost HVS1, clocked at over 2.2 million miles per hour, fast enough to travel from Earth to the Moon in under 6 minutes. If that doesn't make you rethink the raw power of black holes, consider this: every hypervelocity star is a fossil of some ancient cataclysm, a testament to the violent ballet of gravity that orchestrates the cosmos. So next time you gaze at the night sky, remember, somewhere out there, a star is screaming through the darkness, carrying secrets from the heart of a black hole's fury. What if the universe's most elusive substance, dark matter, has been hiding in plain sight this whole time, not as some exotic particle, but as countless ancient black holes forged in the Big Bang's first moments? The idea sounds radical, but it's gaining traction among physicists desperate to solve one of cosmology's greatest mysteries. Dark matter makes up 85% of the universe's mass, yet it refuses to interact with light or ordinary matter. For decades, scientists hunted for hypothetical particles like WIMP or actions to explain it. But what if the answer isn't tiny at all? What if dark matter is made of primordial black holes so old they predate the first stars? The theory traces back to the universe's infancy. In the chaotic aftermath of the Big Bang, density fluctuations could have collapsed directly into black holes without needing dying stars. Some might have been as massive as planets, others as light as asteroids. Unlike their stellar-born cousins, these primordial black holes wouldn't be tied to galaxies. They'd drift like invisible ghosts through cosmic voids. Most intriguingly, if they fell within a specific mass range, say, between the Moon's mass and Jupiter's, they could explain dark matter's gravitational effects without any new physics. No exotic particles required, just black holes we've overlooked because they don't glow. But how do you find something that, by definition, emits no light? The answer lies in microlensing, a cosmic detective trick that exploits gravity's magnifying power. When a primordial black hole passes between us and a distant star, its gravity bends the star's light, causing a temporary brightening. The duration of this flicker reveals the black hole's mass. A moon-sized one might lens a star for minutes, while a Jupiter-mass monster could last years. Projects like the Optical Gravitational Lensing Experiment, OGLE, have scanned millions of stars for these telltale flashes. The results frustratingly ambiguous. OGLE spotted a handful of unexplained microlensing events that could be primordial black holes, but they could also be rogue planets or dim stars. Even more tantalizing, LIGO detection of surprisingly heavy black hole mergers revived the idea. Some of those colliding giants might have been primordial relics. The math is seductive. If just 1% of dark matter were primordial black holes, it would mean trillions of them lurk in our galaxy alone, each a frozen remnant of the universe's fiery birth. Yet skepticism remains. Primordial black holes would have influenced the cosmic microwave background, the universe's baby picture, in ways we haven't observed. They'd also distort the distribution of galaxies more than we see. Still, the hunt continues. New telescopes like the Vera Rubin Observatory will scan billions of stars for microlensing hints. And if even one primordial black hole is confirmed, it would rewrite cosmology's rules, proving that the universe's missing mass wasn't hiding in the lab, but in the darkness between the stars all along. The irony is delicious. The very objects we thought of as cosmic destroyers might be the glue holding galaxies together. And if that's true, the darkest corners of space aren't empty. They're teeming with black holes older than time, silently shaping the universe from the shadows. So there you have it, 30 mind-bending truths about black holes that prove reality is stranger than fiction. From cosmic lullabies sung by gravitational monsters to entire universes possibly nested inside them, these enigmas remind us how little we truly understand. Think about it, black holes rewrite time, spit out stars like bullets, and might even hold the missing pieces of dark matter. We've photographed their shadows, heard their collisions echo through space-time, and yet every discovery peels back another layer of mystery. Are they portals, quantum computers, the universe's way of hitting a reset button? The closer we look, the more questions we uncover. And let's not forget the biggest plot twist of all: black holes aren't just destroyers. They're creators, architects, and even storytellers, sculpting galaxies and seeding the cosmos with gold. They defy our laws, mock our intuition, and dare us to rethink everything from the nature of information to the origins of existence itself. But here's the kicker, this is just the beginning. For every fact we've uncovered, there are 1,000 more waiting in the dark. So tell us which revelation left you speechless: the black holes spinning spacetime into knots, the rogue giants fleeing their galaxies, or the eerie possibility that we might be living inside one right now. Drop your thoughts in the comments below, and if you're hungry for more cosmic wonders, hit that subscribe button. The universe has plenty more secrets to share, and we're just getting started. Until next time, keep looking up. The next big discovery might be closer than you think.